Now we're going to change gears just a little bit. And the reason we're changing gears in 6.3 to gravity and in 6.4 to friction is we can't do much unless we get a little bit more specific and have some example forces in play for you guys to play around with. So one of them is gravity. So here's what you know about gravity so far, both from doing experiments in lab and from reading the textbook. For any object, okay, it doesn't matter if it's a box or a cannonball or a feather. For any object, if you can neglect air resistance, then its acceleration in the downward direction is g. And the way we write that, assuming the coordinate system is set up so that y is up, the way we write that is we say that a sub y is equal to minus g. And it happens that on Earth, g is 9.8 meters per second squared. On the moon, it's about a sixth that much. So g is a positive number, it's 9.8 meters per second squared, and a sub y is minus g. That's what we know about gravity so far. Now suppose we have a free fall situation, and suppose that there are no wind resistance or any other dragging type stuff that you have to worry about. Well, then F net is just F sub g. F net is by definition in that situation, the only force on the thing is Fg. Now let's combine this fact that Ay is minus g and g is 9.8 meters per second squared with the fact that in free fall F net is equal to Fg. We're going to combine it by using Newton's second law. Newton's second law says Fg is ma. But down here we see that the only component of a is in the y direction and it's minus g. So that means we've got m times, well, to make a vector in the minus y direction, we're going to need a minus j hat. And to make this vector have this length, g, it's going to have a g there. So what we just learned is that for a particle in free fall, F sub g is apparently minus mg j hat. Now let me make a distinction between weight and mass. The weight of a particle of mass m is going to be mg. We're going to call that the weight. And we're going to distinguish that from the mass of the particle, which was just m. So that way, if we take a particle to the moon, where gravity is weaker, its mass is not going to be changed once we get there. But its weight will be less because g on the moon is a smaller number than g on the Earth. Now I'll tell you, this is very much in contradiction to everyday use, okay? So if you go to, say, Europe or some country that uses the metric system, doesn't have to be a European country, and you say, I want to buy 200 grams of ham. Well, how do they sell you 200 grams of ham? They get out a scale, and they put your little pile of ham here after it comes out of the deli slicer onto the scale, and they figure out how much it weighs, okay? And inside the scale is actually a bunch of little springs, okay? So what's really happening is a scale is a force detector, not a mass detector. So what they really did there was they sold you not 200 grams of ham, but they sold you an amount of ham that weighs 200 times 9.8 meters per second squared. Okay, and I'm going to convert 200 grams to kilos so I can keep using the metric system. That's 0.2 kilograms. Okay, so we've got 1/5 of 9.8 newtons. 1/5 of 9.8 newtons, which is a little less than 2 newtons. So what they really sold you was an amount of ham that creates 2 newtons of force on the scale. And of course, since we're all buying and selling our ham on the surface of the Earth, where g has value 9.8 meters per second squared, then selling someone 1.96 newtons of ham is the same thing as selling them 200 grams of ham. So that's an important distinction to keep in mind as we go to places with different amounts of gravity. If you're already feeling distantly challenged, just go to 6.3 and make sure you understand all of this stuff that I laid out here. But if you want to go a little bit further, in 6.3, Ninth also has you do Newton's full law of universal gravitation, which tells you how strong gravity is when you're not right at the surface of the Earth. It turns out gravity gets weaker. Not rapidly weaker, but weaker as you go up, away from the surface of the Earth. And then he goes on and does even another kind of interesting thing, which is he tells you how your weight on a scale would change if you put that scale in an elevator and had the elevator accelerate either up, like if you were starting on the first floor of Galileo and accelerated up so you could start your way to the second floor, or maybe you're on the second floor of Galileo and you push the one button in the elevator, and then right after you do that, the door closes and you accelerate down. While the elevator is accelerating, if you had your ham sitting on the scale on the elevator floor, you'd find that the reading changes. And he derives how much? The number one take-home point from this chapter, though, is that gravity's strength is mg, and it's in the minus j hat direction if you set up your coordinates so the minus j hat direction is down.